All right, I think we're ready for Jakob and Maxime, who is going to beam us through the data path. Go for it.
This way? Ah, nice. Thank you. Hello, everyone. We are going to talk about how we brought VDUSE to OpenShift virtualization today. Let's see. Yeah. Okay, so first we are going to describe our mission, and then we are going to describe what we did already last year for containers, and then the new stuff, which is virtual machines. And then Maxime is going to explain how we do this in detail. Afterwards, we are going to talk briefly about workload partitioning if we have time, and then show the interesting numbers. So what do we want to do? So we are going to replace the kernel user space and the kernel stack, networking stack with user space. So we want to see how far we can get if we move everything from kernel space to user space. This means we are going to enable DPDK in OVS. Then we use NetDev bridges instead of system bridges. We use DPDK for OVS to talk to the NICs. And we use VDUSE instead of vETH devices for providing container networking. Well, this was already part of our last year's presentation. Today, we are going to talk mostly about how we do this for virtual machines. So we want to use VDUSE and vHost VDPA instead of tab devices and SAV or similar things for connecting virtual machines. And then talking about how we can properly isolate system from the network from workloads. So, I mean, why are we doing this? Hopefully because we can improve the performance, reduce the latency, and make it easier to, well, separate compute resources so that we can give specific cores to the network, for example. And we don't want to lose features. So in particular, live migration. So if you think about our solution, it's like in between OVNK and SAV. So OVNK is super flexible, provides a lot of features for the user, and it's easy to configure compared to SIOV. So SIOV is on the other extreme, on the right side. It provides like low latency, high performance, but for example, you lose live migration, or at least the way that you usually understand live migration. And yeah, you're on your own. You have to do a lot that OVNK, for example, is providing. And we are in between. So, and this is like, could be interesting for telcos or customers from VMware that might consider migrating. And they might expect certain features that we can provide. Well, and users that have real-time networking requirements. Okay, so now a quick recap of what we presented last year. So this is an OpenShift node, looking at the network of an OpenShift node. So you have BRX on the left side. It's an OVS bridge, and then the oven integration bridge. And by default, you use your kernel driver to talk to the NIC. Then you have a patch port to connect both bridges. And the oven integration bridge, well, has a couple of bridges, but most importantly here, you have vETH device pairs to provide ETH0 in the containers. Now, what did we change last time and this time as well? So we have our bridges completely in user space. So only OVS DPDK, and then we use DPDK on the left side to, let's see. We use DPDK for talking to the NICs, and the interesting part here is the right side, where we have VDUSE devices. So we have VDUSE devices in OVS and VirtualNet, NetDev in the containers. And although the control path is of course handled by the kernel, well, the packet exchange is through user space, not depicted here. Now, what did we change for virtual machines? We are going to focus on the right side here now. So this is like if you set up a KubeVirt virtual machine with default pod networking and masquerading mode, what you get is a QEMU VM that's running in a Virt launcher pod that's connected through a tab device to a kernel bridge inside the Virt launcher pod. And then you have your ETH0, a vETH device pair, and this is doing masquerading to let the VM communicate to the world. Well, and this kernel bridge is also available if you use a bridge mode. Then the E0 is just plugged into the bridge. And this kernel bridge is also available, well, used in user-defined networks, OpenK secondary networks. And it only changes when you have SIOV. In that case, well, you have your NetDev, SIOV VF NetDev, that the QEMU VM can use to talk to the network. And oops. Well, if you use the VFIO PCI mode, you have a chart device. And now this is our new approach. So one different thing is now you see that, again, we have your OVS TPK bridge here on the left side. We have a VDUSE port. And then we have a vhost VDPA chart device in the Virtual Launcher pod. And the QEMU device, QEMU VM, is talking through that chart device with the VDUSE port. So again, control plane is through the kernel, of course, but the packets, they are exchanged through shared memory. So you have a word queue and shared memory between the OVS process and the QEMU process, and the packets are going through that. How this is working in practice, well, this is Maxime is going to explain that.
Thank you. So, so now we have a deep dive into the user space Datapath. It's again a quick recap from last year. So why would we need to add support for user space Datapath in OCP and OCP virtualization? OVS kernel is a good fit for a lot of use cases, but sometimes, thinking about telco use cases, for example, we might want to have better partitioning where we want to isolate the network infrastructure for the workload from the workload itself. We would like also maybe to bring more determinism by providing more predictability of the packet latencies, and also we might want so as Jacob presented, there are solutions like SRIOV for secondary workloads, but we might want to have a unified data path for both the primary and secondary workloads. And yeah, that's where we bring VDUSE. VDUSE stands for VDPA device in user space. At the origin of VDPA, it was only meant for physical devices. For example, you have NICs from Mellanox or Marvell that support VDPA. A VDPA device is a device that implements the VirtIO specification for its data path, but for the control path, it can remain vendor specific. And to drive this, to have a generic solution in the end, the VDPA device drivers implement VDPA callbacks to translate VDPA commands into vendor-specific controls. VDUSE, however, is an entirely software solution. It is split in two components. You have the kernel VDUSE driver, which connects to the VDPA bus, and you have a user space application that implements the VirtIO device. So it implements the ring and links and yeah, everything. So here it's the architecture of this solution. The device is implemented, is hosted by OVS, OVS DPDK. But more particularly, it's implemented into the DPDK VOS library. The good thing by doing this is that we reuse the data path implemented for VOS user backend in OVS DPDK. So that's data path that's already mature, that's used in production. So that's good. Also, by reusing the DPDK VOS library, we inherit from its API, and so the integration into vSwitch is it's nearly seamless. So in order to initialize and configure the device, some chart devs, when the chart dev per device is created, and all the configuration is done using IO controls. The rings, the VirtIO rings are directly mapped from the workload, and And there is also some syscalls like write and reads that are used to when the VDUSE kernel driver wants to notify. So there is a messaging system between the VDUSE driver and the VDUSE device. So when the device is initialized, it can be attached to the VDPA bus. This is done via netlink. There is a netlink tool in IP root that is available if you want to do it manually. And when it's attached to the bus, we have two possibilities, as Jacob mentioned before. You can either bind it to Virtualization VDPA driver. In this case, you obtain a netdev, Virtualization netdev that you can pass to the pod network namespace. Or you can bind it to VIOS VDPA driver. In this case, you get another char device, a VIOS VDPA char device that can be used when you have don't have virtualization. It can be used with CNF, for example, an EDPDK workload that would use a Virtualization user PMD. And in the case that we are presenting today, it can be used with QEMU because QEMU implements a VIOS VDPA backend. So now that we have put the foundation of our solution, Jacob, we talk about workload partitioning. That is another important topic.
Yeah, okay, so we presented two parts already. So one is for containers, second is for VMs, and then we have a third component which is optional, but I have to highlight that. So you can use our stuff without that. So by default, if you enable workload partitioning in OpenShift, you get two separate sets, a set of isolated cores and a set of reserved cores. And well, workloads, if you use, for example, if you have guaranteed QoS pods, they are only allowed to be scheduled on isolated cores. If you have, like the system service, they are only allowed to be scheduled on a reserved cores. But this boundary here, like it's a bit, it's not strict. So for example, if you have the burstable and best effort QoS pods, they are allowed to run, well, mostly everywhere. And we wanted to change that. We wanted to carve out a third partition that's used only for the network, exclusively for the network. We want to make it like that. So we had to enhance the performance profile API of the node tuning operator. So this is pretty OpenShift specific. To make sure we have a third component, those core 2, core 2 in this case, where only our OVS duplicated PMD threads are scheduled. So nothing else. So our networking is handled only on that core. We made also sure that best effort and burstable pods are not allowed to run on the system cores. So we have this reserved set of cores. Only system services are scheduled. And that's why are we doing this? Well, we want to improve the performance, right? That's the reason for it. But it's optional. We can just skip that if you don't need that. And now up to the numbers.
Thank you. So now I will present some initial benchmark results and the optimization we did to improve the performance of this solution. So we'll start with internode VM to VM benchmark. So we have two VMs running on two different worker nodes. And so what sorry. So the traffic, okay. So the traffic goes from one VM. It goes through a connecting 6 DX device, so MNX5 PMD, through a GNIF tunnel and go to the other VM. It's running some classic Xeon CPU. The base for this benchmark is OpenShift 4.19 plus some patches that were needed to bring this POC up. OVS is 3.5 plus some fixes and optimization that I will mention after. And the VMs, our classic VMs are not really tuned. We have two vCPUs, 2 GB of memory, and no huge pages, and no vCPU pinning. So first, let's start with the internet TCP benchmark. So using Hyper-3 TCP. So what we can see is kernel Datapath outperformed our initial results for larger buffers. So that was not what we expected initially. By doing some investigation, we noticed that we were doing software segmentation, whereas we expected to do to offload this to the ConnectX device. So David presented this earlier, but yeah, David fixed these issues. So now we can offload the segmentation and the checksum offload to the device. Yeah, I invite you to review David's talk if you want to have more insight on this solution. Another issue that we noticed that we saw quite some TX drop on the VDUSE port, so on the host side. We saw that the devices were only using 256 descriptors. Usually when we use OVS DPDK, we use 1K descriptors. That's what is suggested to our customers. So we try to change that. It's not currently possible to do that by configuring KubeVirt. But for the purpose of this POC, we just patch QEMU defaults and rebuild QEMU. So with these changes done, we recover part of the gap we have with the kernel solution. We are still not at the same level. And for smaller buffers, we are better than OVS kernel for up to 2K buffers. We are better, but while debugging, we noticed that we forgot to remove one debug option, one option that we set when we developed the solution initially on virtual machines to not overload the host CPUs. So the PMD sleep max option was enabled. If we disable it, because it was not really intended to have it enabled, we notice that the performance actually decreases for smaller buffers, but improve for larger ones. So how do we explain performance is better when we introduce sleeps into Datapath? Our assumption is that when introducing sleep, we improve the batching, and so we reduce the number of interrupts that we are injecting into the guest. So, and in turn, we reduce the vCPU load. It has less interrupts to handle, and when it handles one interrupt, it handles more packets. So we did some profiling with small buffers where when PMD sleep max is enabled, we have better performance than when it is disabled. And we can see that when this option is enabled, we reduce the number of interrupts by a factor of 30, and the CPU load is twice smaller. So we get better performance with a smaller number of interrupts and the lower CPU load. So the question now is, how do we reduce the number of interrupts so that we get a good performance for small buffers while keeping the better performance for larger ones? So the solution we have worked on is a IRQ coalescing feature from the VirtIO spec. It enables the driver, Virtual driver, to request the device to only inject an IRQ every X packets or after a timeout has expired. It is supported in the upstream kernel in Virtual driver for both the RX and TX queues. So for TX queues, the interrupt is used for recycling the buffers that have been transmitted to the host. In DPDK, it was not present in the VS library, so we had to prototype it. So if you look at the advantage of such solution, so it should normally have the same impact in terms on the interrupts, number of interrupts and CPU load that introducing sleep in the Datapath. On the drawback side, it will have an impact on if you enable it on RX queues, because you have less interrupts. Okay. So with this enabled, we can see that in purple, we again recover. So for smaller buffers, we are as good as we are better than Canal Datapath, and for larger ones, we are almost as good, but not yet. If we look at the UDP benchmarks, before the optimization I mentioned earlier, we were already better, and we are with optimization twice better than Canal Datapath. Latency using TCP, netpair TCP error test, we see that the mean latency is twice better for the optimized DPDK datapath. But more importantly, if you remember, predictability was one of the concepts that we were trying to address. We can see that our datapath is much more predictable. The max latency is an order of magnitude lower with the optimized DPDK datapath. And then that's not a surprise, but for DPDK test PMD, this use case, when you use VDUSE, has no interrupt into the picture. So it's polling mode into the guest and into the host. So, but when you use OVS kernel, you still have interrupts to notify the host, or it's not interrupts, but it's notification to notify the host that packets have to be descriptors have to be dequeued. So here we are much better. So we have run the same test for intranode benchmarks, but we don't have a lot of time, so I will skip them. So I'll go through them quickly. With for intranode benchmark, so it means that we don't have GNIF tunnel, physical NICs, so it's both VMs are running on the same node. So we are much better than Canal Datapath for smaller buffers, and still better on par for larger ones. Same for UDP. Latency is again in the same range as the previous internode test. And yeah, for DPDK, we have a factor of 8 between OVS DPDK and OVS kernel. So for DPDK workloads, if you have a VNF that you want to run on KubeVirt, that could be something to consider. So I will now give the mic to Jacob for the conclusion.
Yeah, so to sum up, well, hopefully you saw that our performance is pretty good for certain parts, but this comes at the cost, of course, which is complexity. It's more difficult to configure this stuff than just taking the default OpenShift. And we have a couple of plans what we want to do in the future. First, we want to finish up our to-do list, in particular, finish the live migration part, develop a new CNI that moves our solution closer to SIOV, so less features, more performance, and finally, like, take our 3 components and make solutions for different customers. One thing I want to highlight is, well, Maxime and I are presenting this, but this has actually been a pretty good team effort by several teams and several orgs. So these are all the people that have been involved. I hopefully didn't forget anyone. So really, thank you, guys. This was awesome. That's it. Questions?
Just to make sure I got it right. So basically the performance using a non-DPDK workload, which means regular kernel network, we can be the OVS DPDK with VDUSE can be a par with the kernel network.
Yes, indeed. The only benchmark where kernel Datapath outperforms DPDK, we'll scroll back, is the TCP between 2 nodes. So here we have, yeah, we don't understand yet why yeah, sometimes the TCP stack can be a bit finicky, depending. Yeah, so, small changes change the performance a lot sometimes. So yeah, we still need to investigate this. I would like to highlight also that we have done some optimization on the VDUSE datapath or the PDK datapath. Some of them could be also applied to the OVS kernel, like increasing the number of descriptors could also be done. I might have an impact also, but we have not tested it. The same for IRQ coalescing, so it would be much more complex than for DPDK datapath, but in theory, that could also be possible.
Okay, so this is showing that for TCP workloads, without the PDK, the performance is quite good, especially for the small packet size.
Yeah, indeed.
All right, and can you move to the DPDK workload? Right, so this is now DPDK inside of the VM, right? So we have a DPDK specific workload inside, but in the same thing that you tested with the kernel, but now you are only changing the workload inside of the VM.
Yes, yes.
Everything else is the same.
Yeah.
We have a question online. Alex, do you want to ask live?
I just wanted to know, it would be nice to know how OS kernel is tuned in these tests, because you can like tune how RQs are arranged to cores, and you can tune a lot of things in OS kernel to make it faster actually. So what are we comparing to?
Yeah, so we have used the default tunings done in OpenShift. I'm not sure exactly all the tuning that have been done for this part.
Yeah, so what we did is basically take the telco specs and apply that to our cluster to make sure that, well, we have the optimal tuning. This means, for example, as I mentioned earlier, carving out those threads that are only used for our workloads, make sure that no hardware interrupts are being, no interrupts are being handled by those cores, and what else you can do. What I mean is we did everything that we could do to maximize performance, but we kept that for both benchmarks, right?
Mm-hmm.
So for the kernel benchmark and the DPDK benchmarks, otherwise it would be a bit unfair.
Mm-hmm. Thanks.
For the obvious DPDK use case, so you introduce a new type of native VDUs, or that is based on the vhost user, or just the plain vhost user DPDK?
So for the host part, you mean? So the part that is
No, for the obvious DPDK part.
obvious DPDK part, so it's using the vhost DPDK vhost library.
The native one, or you
Yes, the native one. So it's only the optimization for IRQ coalescing have been added for this POC. All the other parts, the VDUSE backend, control queue support is already in upstream DPDK.
I see.
Basically, when we say POC, this means that all our changes for OVS and kernel and such are upstream, except for the one feature that Maxime mentioned. But all the parts on OpenShift, they are not merged yet. So all the Kubernetes and OpenShift specific stuff, like for example, the workload partitioning, they have not been merged yet, but the rest has. We also didn't merge yet the OVNK patches.
So I was going to ask why you CNI, but then you said you didn't merge OVNK patches. So what's the plan then?
Okay, so we want to tackle different use cases, right? So one is we want to see how far we can get if we take a stock OCP and then replace OVS kernel with OVS DPDK and such. So keep all the features from OVNK because it provides a lot. But then we also want to see how far we can get in terms of performance by, well, dropping OVN and others. Of course, you lose features, but maybe you gain some performance.
Okay, so thanks.
Yeah, also there are limitations currently in OVS DPDK that would make it not work perfectly in the Open Kubernetes with the Open Kubernetes pipeline. So it's kind of easier to have an independent OVS DPDK rather than changing the entire Open Kubernetes over to user space.
I have one more question. So going back to IRQs and reducing IRQs, you were talking about IRQs in the virtual machine kernel, right?
I'm not sure what.
Yes, yes. So what the IRQs that the VirtualNet device driver within the guest receives.
Thanks.
So in these IRQs, when you have you use VDUs, are syscalls, IO controls made by OVS, so by the DPK VS library, so by the PMD threads.
Thanks.
Hi, thank you for your speech. Would you please answer, you tune coalescing settings for the PTK case, yes, and to achieve better results. But did you try to tune the same settings for the kernel case to have more fair comparison, for example?
Yeah, so that's what I mentioned to Flavio when he asked his question. So doing it for the kernel Datapath, meaning adding support for IRQ coalescing in the host kernel, could technically be possible, but we have not done it, and it would be, in my opinion, much more complex to implement than in DPDK. But yeah, today the kernel solution does not have this feature of VS kernel, I mean.
Any last questions? Okay, let's thank our speakers again.